In many of their reactions, diols and triols behave relatively similarly to the alcohols with just single hydroxyl. But now we'll talk about two reactions which are unique to diols and which actually unique to 1,2-diols and take advantage of this quite specific arrangement of two OH groups. And the first reaction we'll discuss is the so-called pinnacle rearrangement. Pinnacle rearrangement has been named after a compound, this diol, which has two OH groups right next to each other, which is known as pinnacle. And quite early on it was noticed that to expose this to, say, sulfuric acid at elevated temperature, you will end up with a rearranged product that looks like this and known as pinnacolone, along with the elimination of water. Mechanistically, this reaction starts as expected by protonation of one of the OH groups, which is then followed by the departure of that OH group as water and the formation of this formally tertiary cation. And in many cases, we would have seen this cation as perfectly stable and the reaction would not rearrange. But in this case, we see a rearrangement of this cation to give us another kind of a tertiary cation, which is now oxygen-based. And this is really the key to its stability because this neighboring oxygen allows the stabilization of this cation through resonance to give us this resonance stabilized cation, and now loss of hydrogen of proton from this cation gives us our final product. This is one example where not only hyperconjugation plays a role in stability of cations, but also resonance. As we know, resonance is a much more significant effect, and so this is why this reaction is exclusively driven to pinnacle. Another reaction which is unique for diols is the so-called periodic acid cleavage. This again occurs in only in 1,2-diols, and if we start with this cyclohexane Y2-diol and treat this periodic acid HiO4, then we will get an intermediate in which the central iodine is bound to many oxygen atoms, and the rearrangement of this intermediate will cleave the central CC bond, place this electron pair onto iodine, and reform another CO bond. And after elimination of HiO3, which is no longer periodic, but instead iodic acid, we will get to this aldehyde. And this reaction in a way is complementary to ozonolysis, because now we can start with an alkene and get to a dialdehyde, either by treating this alkene first with ozone and then with dimethyl sulfide, or by two-step oxidation, where we first convert this alkene to osmium tetroxide, hydrogen peroxide, into a diol, and then we convert oxide to diol using the periodic acid. Both of these methods are used quite frequently. Now in the next couple of sections we will see how alcohol reacts with various types of acids, both organic and inorganic, to give us compounds known as esters.